Hello, I want to go through this document to give better background about this project. The basic idea is that there are two types of bird abundance measurements being made: point counts and transect observations. These two contain related information. By comparing these two, we may gain some understanding about the system and estimate some values about the system. There really are two parts to the paper. The first part uses a model of bioenergy consumption. I should say uses two models of bioenergy consumption. One model that uses transect observations, and one model that uses point counts. By comparing these two models, we can estimate system parameters. This model depends on the transect observation, which is the bird eating the fruit, and we make a model that the bioenergy consumption depends both on the fruit weight and on the bird weight, as well as on the number of times that the bird is seen eating the fruit. Okay, fruit weight times, number of times that the bird is seen eating the fruit times the fruit weight to some power times the bird weight to some power. So this is a fitting model that we will use regression to fit. So that's one model. The other model is, well, this model simplifies by moving all fruit species together and simply using the mean fruit weight instead of the fruit weights of the individual fruit species. The mean fruit weight is achieved by a weighted average in this equation. All right. Here's another model. The bioenergy consumption depends on the point counts, which is a measure of the bird abundance, times the bird weight to some power. Okay. Notice that both models depend on the bird weight to some power. Now, if we set these two bioenergy consumption estimates equal, we can gain some information about the parameters in the model. The reason we do this is we cannot estimate exactly the energy consumption, but we can compare these two models and see what that tells us about the parameters. So here we set the two models equal, and then we take the logarithm. So we get this model here. Right, we have the term that depends on the transect observation, point count, and then a constant, another term that depends on the bird weight, another term that depends on the fruit weight, and then this is the error term. Right? So the point is to estimate these parameters, C0, PB, and PF. Now, the first part, does this fit? And we show that PB that PF seems to be no different from 0. So we remove the PF from the model, and we have a simplified model. Okay. Now, what we would like to do is use the point counts and the transect observations and combine these two to get a better estimate of the relative abundance of the different species. So we have a basic model of abundance, that abundance is proportional to point counts. K is a constant of proportionality, Zn is the point counts. This is the error term. Right? So since we're only interested in relative abundance, the K is not important. Because if I take two different species, suppose I take A1 and A2, If I take the ratio of A1 and A2, then I have a k in the numerator and the denominator, and those cancel out. So I'm really not interested in the value of k. So instead of estimating this abundance completely, I can estimate this, I can call it scaled abundance, which is the total abundance divided by k. So I do not need to worry about the constant of proportionality. Now this model depends on the point counts. Now using the model here, the equivalence here, that relates xn to zn, I can solve for zn and replace it with terms involving xn. So if I take the exponential of both sides and I solve for zn, then I get an expression for xn in terms of zn. I get an expression for zn in terms of xn. And I get this alternative model of the relative abundance. All right, now I do not know the error terms, but I can estimate this relative abundance by taking my measured value of zn and by taking these parameters times my measured value of xn. Now these parameters were estimated by the regression in the section above. Okay. So in this case we're estimating abundance. We can also estimate log of abundance. It turns out that this is mathematically easier. Well, we will do both. So here's the log of the abundance. We can estimate the log of the abundance by the log of my measured point counts, or by these parameters plus the log of my measured transect observations. Okay. So I have two different ways of estimating the same thing. So what I would like to do is combine those two estimators and get a more accurate estimator. Just like in science, you take multiple measurements and you use some average or some combination of the multiple measurements to get a more accurate measurement. In order to test this, we want to test it on some simulated data. We cannot test with actual data because we do not know the true values of the log of the abundance. But we can simulate and generate simulated values of log abundance. And we can generate the Zn, the Xn, and the C0 and the PB. And we can see how to combine these two estimators to get a better estimate of the actual log abundance. All right, so in the following, I'll work with a log abundance. All right, this figure is about some things before. All right, so here we are talking about combining the two estimators, one based on the point counts and one based on transect observations, to obtain a estimator that perhaps is more accurate. And we will do experiments to discover the best value of beta. In fact, that should be beta n and not beta. And there's a mistake there also. I will fix this later. All right. So these are the steps. So far, I think that we have generated the simulated data. We take Zn, we take simulated point count, and we simulate the transect observations. Right. Now, what we want to do then is to use these parameters to estimate the regression parameters in this equation here. Well, this equation 8 is up here. So what we need to do is use the new values of x and z and perform a regression on this relation to estimate C0 and PB. Now, to estimate these two parameters, C0 and PB, we need to rearrange this equation. And that's done down here. I bring the Zn over here. So this log xn minus log Zn is treated as my dependent variable. And this dependent variable depends on C0, which will be my intercept, plus PB, which is the coefficient I want to estimate, times log of Bn. Log of Bn, I know, these are the bird weights. The error term you do not put in the regression. The error term comes out of the regression. So using this is my dependent variable, and I do regression with intercept, and my independent variable is log Bn. I can estimate these two parameters C0 and PB by doing a regression. Now you can find regression in Python. Scikit-learn has a regression. If you look in this code, there is a regression implemented here. It would be good to try to understand how this works. This is line 130 of ABproj.ct. And this is using linear regression from scikit-learn. The input was up here. Okay, so that's one way to do linear regression. I think there are other linear regression functions as well. But what we want are the regression coefficients, and we're doing a regression with intercept because C0 is our intercept. Now, once we've estimated C0 and PB, all right, so I explained that a little bit here again. Log xn minus log zn is the dependent variable, and log bn is the independent variable. C0 will be the intercept. So using the values of C0 and PB, you may compute the ln's. This actually should be x and not z. I'm sorry. Because the ln x requires C0 and PB. Let's verify that. That should be x. Let's go up and see. You can see ln of x depends on C0 and PB. All right, so if I have C0 and PB, I can compute both of these estimators for the simulated data. All right. So I want to return from my function, I want to return all four of these estimators. The log estimator from z, the abundance estimator from z, the log estimator from x, and the abundance estimator from x. So that will be my complete function. We will call this function a large number of times. I say call that n iter. Each time you call the function, you will return 4 values. So we can store the results from the loop in an array that's of size n iter by 4. Once we have this array, then we can find the best combination of the two estimators. All right, but for now, what we need to do is do the linear regression, finish the function that has 4 outputs, write a loop to call the function this many times. All right, so that's good for right now.